All right. Yes, presenter view. All right. Good afternoon, everyone. My name is Kent, and today I'm here to talk to you about Multicore, seL4, and verification. So we all expect that our operating system kernels are going to provide us access to the hardware that we run on. And over the last 20 years, multi-core systems have become incredibly proliferate, very common. And however, the state of the art for verified seL4 is still a unicore system. So that means that if I want to run on a multi-core hardware platform, I can only use one core at a time. And so as you can see here, lines go up, lines stay flat. That'll be the only graph in this presentation. So what are we doing about it? Well, currently we have the SMP configuration, which is unverified. It presents a single system image, so the kernel, a single kernel runs across all of the cores of the platform, and it presents a single abstraction to applications running on top. So it supports multi-core applications. It's easy to move resources across cores, and IPC, so like endpoints, notifications happen sort of transparently, whether it's on the same core or on cross-core. However, this means that there's concurrency in the kernel because each application, regardless of what core it's on, when it calls into the kernel, it's calling into the same kernel. So from the kernel's point of view, there can be multiple threads of execution for the different hardware cores running on it at the same time, which means that verification is non-trivial. I guess you could say that it's verifiable, but the time until it's verified is a long time in the future. And for someone that wants to use seL4, the verified configuration, I can't necessarily do that until the verification is done, because if you can't prove that the concurrent access in the kernel is safe, then potentially anything could cause like the functional correctness, you don't really have it anymore. So what I'm reintroducing here today is the partitioned multikernel. So multikernels were introduced in Barrelfish about 10 years ago. Okay, sorry, 13 years ago. And it was also prototyped for seL4 in a PhD thesis by Michael von Tessen. The clustered multikernel, or in this case, a partitioned multikernel, runs a separate seL4 strongly partitioned on each core. So the other kernels running on other cores appear to the primary kernel, or like appear to any other kernel, as just different devices running on the system. And there's no concurrency in the kernel. And what that means is that verification can still use a sequential model, and applications can run on top. Because verified kernels, because the kernels can't trust user-level apps to tell them about kernel resources, you can't dynamically move resources across kernels at runtime. So that's sort of why it's like a fully partitioned static kernel, where the kernel resources are partitioned from the start, but you can move applications across by implementing it at user level. You can do cross-core communication at user level. And basically, as verification becomes more able to deal with truly concurrent executions and the framework gets updated, you can start incrementally moving towards SMP. What that means, like most importantly, you can sort of say that provided that the kernels aren't interfering with each other, the unicore functional correctness proofs should still hold, because like the separation between all of the hardware resources. So it's almost no different as if you're taking two kernels, running them on two separate machines, and using the unicore proofs, you know that you trust in those proofs. So now you're just making a distributed system on the same hardware platform. Of course, there are significant trade-offs for having a partitioned multi-kernel system with resources you can't move across cores. But being able to have a verified kernel configuration running on a multi-core system is definitely a plus. So, I mean, basically, in this simple trade-off here, you've got kernel state, which is whether or not the shared state in the kernel is separated or partitioned, multi-kernel partitioned. Concurrency in the kernel, no concurrency in the kernel at all. That means better verification. And yeah, cross-core communications implemented at user level versus implemented at the kernel, also implemented at user level. But basically, the outline for what I'm going to talk about today is going to start by briefly going over the SMP kernel and making my own attempt to explain why the verification in concurrent systems is hard, and then go on to why a multi-kernel approach can be ready much sooner, and then also look at a little bit of how these complications arising from using a partitioned system can be sort of fixed at user level by using a user level framework like CAmkES to sort of still present a single system image to the application or system developer. So basically, here's a very simple model of a sequential CPU. You have a system bus, computer processes a single instruction stream, reads and writes to memory or reads and writes to I/O. There may be some caches. That's roughly what the current proofs model the system as. I mean, I'm simplifying it, but it's still key takeaway, single instruction stream, sequential execution. However, modern hardware systems at least have more than one execution stream, and so you got true parallelism. There's a lot more caches, there's shared caches, there's separate caches, there's maybe more than one system bus, but main point is that there are no longer sequential execution. So how does the SMP kernel deal with this for a user? So when you're writing applications on top of seL4 for a single core system, you get given a bunch of objects and you can create threads, you can give them capabilities to stuff in the system, and then they execute. The SMP kernel basically is the same thing, but you now have additional cores at your disposal to run threads on. And so what that means is that, sorry, laser can't make it work. There's core local data that is duplicated for every core. So that means that each core gets its own ready queue of threads that are currently schedulable. It always schedules the highest available runnable thread of the highest priority. Each core has its own thread that's active, has its own idle thread, has its own flag for rescheduling IPIs. So probably shouldn't have put that in there because I don't have anything to say about it. And then there's core local state for each thing in the system. So it's like some MCS state, so the budget, the current amount of time that the thing is run for, some FPU state, so whether or not it's using the FPU, and some vCPU state if it's a hyperkernel. So like things like what the interrupt controller currently has in it. Otherwise, like notifications endpoints are unmodified. They still have a single global queue where a blocked thread that's blocked on a notification or blocked on an endpoint is potentially on any core. So when you wake it up, it's going to run on the core that it's assigned to. So threads basically have an affinity. So each thread gets given a scheduling context if you're on MCS. And basically a scheduling context specifies the core that that thread is allowed to run on. On non-MCS kernels, this core is actually part of the TCB as an affinity attribute. But anyway, and IRQs, we go from having a sequential number of IRQs to some IRQs which are per processor. So like on ARMs, like the first 32 IRQs are per processor IRQs. So you can create different capabilities for each of those independent IRQs. And you can also specify the target that an IRQ is delivered on for non-core local IRQs, so for like platform IRQs. And basically, that's what it looks like to the user. So you still create threads as if you're using a unicore system, but you can move those threads onto different cores, or you can start them on different cores. Or if you're on an MCS system with passive threads where scheduling contexts can migrate across threads, you get thread migration because a thread can migrate between different cores based on the scheduling context. And so what does this look like from a logical perspective is you have all of these different applications that are abstracted over all of the hardware, and seL4 sitting in the middle. So as I said before, this means that each application on each core can call into the kernel concurrently. So you need some sort of mechanism for ensuring that there's no corrupted state, that the kernels are doing things in a deterministic way. And so for the SMP kernel, we use a single big lock. And what that means is that initially, we wanted to simplify verification by maximizing the amount of code executing in the kernel sequentially. And the easiest way of doing that is using the coarsest grained lock, so that effectively app enters the kernel, it's as if it's on a unicore kernel, and then it exits the kernel and it's done. However, there's still concurrency in the kernel because you have some code for acquiring the lock And there's other difficulties around that. So like when you enter the kernel and you may not want to do something that's touching shared kernel state, you still have to require the lock. So for say delivering an interrupt, you have to take the lock every time. Very pessimistic. It impacts your worst case execution time. So instead of having a worst case execution time that's say like under a few microseconds on a unicore system, your worst case execution time on a multicore system is the worst case of waiting for every other kernel to do an operation and you're at the back of the queue for requiring the lock. So as I was saying, the biggest thing now is that there's concurrency in the kernel. However, the seL4 proofs model sequential execution. So this diagram here is just a classical race condition where you have two threads of execution adding one to a variable and writing it back, and you can get a scenario where you lose one of the writes, or you lose one of the increments. So the proof has to cover all conceptual scenarios where a race condition would potentially impact correctness. So you can either try to prove that all of this code at every step is potentially going to be interfered with other code running and doing updates to the system, or you can introduce mutual exclusion primitives to try to get back to the sequential execution for large points of the system so that you can reuse a lot of the existing proof infrastructure. However, there's still kernel entry code that has to run outside of the lock. And the biggest example of that is when you enter the kernel has to save the registers of the current thread to a memory somewhere, which is that thread object. So if that thread has been deleted by another core, that thread has been deleted by another core, the kernel would be writing to invalid memory. So because of that, other cores are not allowed to delete threads. They have to actually make sure that they talk to the core that the thread is currently running on. I'm sorry, I'm going down a rabbit hole here. My point is that you can't just say that all of the code is in the lock and therefore it's all sequential. There is still code that is going to be concurrently accessed, and so you have to have concurrent proving framework to prove it correct. I should have just said that. In addition, most modern ISAs don't have strong memory models. They have a weaker memory model. So here's another classical weak memory model example where you have two cores that are writing independently to different regions of memory, and there's some sort of store buffering going on, and then they read back the memory from a different core, and even though they've both written ones, they can read back both memory addresses as zeros, which is, there isn't a way that you can order this which is sequentially consistent. And like, I think this is an x86 total store order weak memory model. And what that means is when you're trying to verify concurrent code and concurrent locking primitives, your model also needs to be able to deal with like these weak memory models. And so using this diagram that I found on the Proofcraft website, which I'm sure many of you have seen in earlier presentations, there is a lot of existing work that has been going towards the seL4 theorem, and it's all built on top of a sequential execution model. And so going towards a multicore model is going to be a lot of work just to get to the point where you can use a kernel that is verified under a concurrent system. So, time check. So basically, SMP kernel has shared state. There's concurrency in the kernel. The big kernel lock does simplify verification, but not by a lot initially, because there's still going to have to be all of this work to build the concurrent proving framework. It does add locking overhead to kernel operations. Gernot mentioned that they were going to be looking at ways to address that with the reader-writer lock, but that's going to come after there's already a proven big lock kernel. And yeah, and then non-negligible code changes as well for implementing this SMP single system image design. So multiprocessing on seL4 with verified kernels. Is there a way that we can get a verified kernel running on multi-core systems faster? And to do this, we should say, like, let's try to have no concurrency in the kernel. That means that proofs can still use a sequential execution model. If possible, no changes to the verified C code for the existing kernel. We still need to make sure that it's able to build useful systems with it, because it's no use saying like, we have this multi-core system if it's still just a toy kernel. And yeah, ideally possible to migrate to a proper SMP kernel in the future. So this is where we start talking about the multi-kernel or the partition kernel approach. So instead of having one single kernel image running across multiple cores, we just treat it like a distributed system and have a single kernel pinned to each core, managing threads, where threads run on a single core, and they can only talk to a single kernel. And anything going across core requires hardware mechanisms like shared memory or message passing frameworks, but sort of all has to be implemented at user level using hardware primitives provided by each kernel on each local core, but each kernel is not aware of any other kernel, and it's relying on the other kernels to sort of stay out of its way. So it's got its section of resources that it's using, other kernels have their sections of resources that it's using. In this diagram, we sort of partitioned the CPU nodes. So you have to do the same thing for memory. So here, this is sort of the RAM of the system. So because the kernel provides almost all of its memory management via kernel untypes and device untypes, it's very easy to partition the system up at configuration time or at boot time so that it's easy to show, or it's easy to handwave that the kernels aren't going to be using the same memory, which means that they aren't going to be interfering with each other. They aren't going to be they're not going to be accessing the same state. And over time, that can become less of a handwave and more of something that is actually proven. And so what we've got here is that we've got two kernels, kernel 0 and kernel 1. Those are the kernel images in memory. So it's like the globals stuff that's very static. And then there are two sets of untypes. So in our partitioned world, we have core 0, which has its set of kernel untypes, and it's allowed to use them to create things like threads and C nodes and other magical capabilities. And the other kernel gets its own set of kernel untypes to use for its system. But we can still reserve this big chunk of memory for device untyped, which the kernel restricts access to. Like the kernel will never read or write to device untyped, but it does allow the user to map device untyped in to its own address spaces. So you can use that to create shared memory. And with shared memory, you can communicate. And if you can communicate, you can build multi-core systems. But one thing that I have mentioned is that because the kernels aren't aware of each other, inter-process communication is slightly harder to do. You have to implement it at user level. And so what does this look like? So basically there's sort of shared memory and signaling, where on a unicore and SMP system, you have duplicate frame mappings where you can map the same region of memory into an address space on different applications, and it mostly works. Multi-kernel, it's the same thing, but you have to do a little bit of additional coordination between the kernels to make sure that you're using the same physical memory. Signaling, on an SMP unicore or a unicore system, you have notifications where the kernel is implementing that primitive. But on a multi-kernel system, you can use notifications if you're still signaling on the same core. But if you're going across cores, you now have to use a more of a pure hardware mechanism, which is an interprocessor interrupt, where you can generate an interrupt from one core, the other core receives it, and the kernel already has interrupt handling mechanisms, but you do need a new mechanism for generating interrupts, which I'll get to on the next slide. And so these protected procedure calls or endpoints, basically, you can still use them on the same core, but you can't do endpoints across core in a multi-kernel system. Lots of people say that you shouldn't use endpoints on a cross-core system anyway, but when I say lots of people, I mean Gunnar. But basically, you can implement that using message passing at user level with a combination of shared memory and signaling. So basically, the one thing that you would need to change to an existing verified kernel to do cross-core notifications is the introduction of an authority and a kernel mechanism for generating an interprocessor interrupt. So basically, what happens when you want to signal a notification in this case is you have to, if it's on a different core, invoke an IPI capability. The kernel would then, assuming that you had the authority to invoke this interrupt, it would generate the interrupt using the hardware interrupt controller. The hardware interrupt controller would then deliver the interrupt on the other core. The other core would receive the interrupt, and if that interrupt had been registered with an interrupt handler, the kernel would deliver it on a notification to user level, and you've now, with a little bit extra steps, sent an interrupt from app A to app B. And This is kind of similar to notifications. However, it is a little bit less scalable in terms of resourcing notifications because each notification now is using an actual IRQ number, whereas in a unicore or an SMP system, you can create as many notifications as you have space of memory on the system. But for a IPI, you only have 16 IPIs per core on a ARM system. So if you're wanting to do more notifications, which most large systems you'd have to build some sort of abstraction that can fan that out and build like a logical notification mechanism at user level. But anyway, it's out of scope. So, so IPC is complicated, but we can use a system like CAmkES or any other component architectures like the core platform to manage a lot of the coordination and the setup work to still present a sort of single system image to application developers. Because they're still designing systems as components that are talking to other components via these communication endpoints. And so in this example here, I have a basic CAmkES system of a client and a server, where the server is an adder that just adds numbers together and the client requests it to add numbers together. It's a very trivial example, but it's the first example in the CAmkES repository, so I used it. And I've moved one of them onto a separate core. And so what I'm going to be continuing to talk about is how I've made some changes to CAmkES to make this work. So basically, the first change is you just have to specify which core or which node each component is running on in this CAmkES configuration here. And otherwise, it's still, you're defining an adder component, you're defining a client component, and then there's this shared data and an seL4 notification connector between them, and one going back in the other direction. Now, in addition to that, to your CAmkES spec, you have to define these nodes. And so each node now has the region of physical memory that the kernel is using, a region of shared pool that both kernels can use, but only for device untyped. And on this side, you have different kernel running a different non-overlapping piece of memory and a shared pool that is overlapping. And in addition, you have to tell the kernels not to use each other's regions of shared memory. And so what that means is that when the system gets built down into a collection of CAmkES specs, it can also generate a platform layout or the platform header file based on modifying the platform description, so a platform device tree for the kernel. And so each kernel gets built assuming that it has different regions of memory compared to the other kernels. And then so how this gets laid out in physical memory is you've got your physical address space in the middle here, and you got your client virtual address space and your adder virtual address space. And so client programs are separated, adder programs are separated, their shared memory is the same, and then there's two separate kernels mapped to the address space in each one. And then because device MMIOs are also device untyped, you could have partitioned devices or you could have shared devices if you wanted to. And so then what this happens is this sort of gets built down now when we're actually loading the system is we have these 4 images for 2 cores. And so in a unicore system, these won't be here, and you just have your kernel and your system image, and the kernel loads the system image. Now we have 2 kernels and 2 system images, and so this alpha loader just loads them and initializes the cores separately. So it's still kind of like a single CAmkES file, so it's sort of a single system image, but it's abstracting over these multiple cores. And so then at the boot process, the alpha loader starts up, and now instead of just loading a single kernel, it's setting up each other kernel, and then the system initializes. And it's like after this point, there's no built-in synchronization points between the 2 cores unless it's implemented at user level. So now the system is running. What does IPC look like with CAmkES? And it's like, well, I'm sort of just recapping another slide here. You have your basic RPC connectors, which you can do intra-core. You can't really do cross-core, but you can build it again using these data ports and signaling. Otherwise, data ports work the same way. When you're going intra-core or cross-core, the connector templates, so when CAmkES is generating the capabilities and the glue code, it can detect that the different applications are set on different cores, and so it generates different caps accordingly. So when they're on the same core, it just uses a general untyped data port, but if they're on a separate core, it allocates a region of memory from that shared pool, and then in the CAPDL file for the system A, it's using this shared memory as mapped to this component. And then in the CAPDL file for the other system, it's using the same shared memory mapped to the same component. And the loader then sets it up, and now they're talking. And for signaling, it's similar, only instead of using a notification in a single core system, you can, when you're sending signals across core, generate this IPI receiving capability on one side, sending capability on the other side. So yeah, so basically summary of my experiments into this so far is sort of being able to successfully change the ELF loader to support multiple kernel setups on AArch32 and 64 platforms. So some kernel compilation tooling to tweaking, supporting partitioning the memory and partitioning the IRQ space at build time. This IPI capability, which introduces an IPI capability for generating these IPIs, and then some sort of playing around with some CAmkES extensions on having that single CAPDL file, single CAmkES architect, the CAmkES ADL file generating multiple kernel images. So it's sort of, now it's a distributed system component architecture framework for microkernel embedded distributed systems. So CAmkES does, yeah, sorry, I shouldn't ad-lib stuff like that. And starting to wrap up now. So there's still, one of the things we care about is incremental steps towards verified SMP. So what we have, if we go with this approach, is unicore kernels running on separate cores, partitioned like distributed systems. And you can sort of make an argument that the unicore proofs can still prove functional correctness, but you can't prove that the system as a whole is still correct because the proofs aren't aware about these multi-core systems. And so you'd say that we're sort of hand-waving a bit there. But by building out the concurrent verification frameworks, we can reduce that. And when I say we, I don't mean me, I mean Proofcraft and other people of the seL4 Foundation. We can build out this verified concurrent proving framework and actually start shrinking more and more of the assumptions about this multi-core system, this separated multi-core system, until we are proving about making claims about truly parallel systems. And then we can actually start adding in little bits of SMP style stuff. So starting with something like a unified domain scheduler, where so the domain scheduler has a domain that switches at a specific time or a specific schedule, and only threads of a particular domain can run at that time. And for a multi-core domain scheduler, you sort of want that to be a, what's the word? Like a full system scheduler. So it switches all cores at the same time, which means that you need to synchronously make that switch from one domain to the next domain, where implementing that is sort of, it's an atomic variable that you want to increment, and you want to have a barrier to make sure that all of the cores, all of the kernels wait until that thing has been incremented, and then they see the update, and then they can continue executing. So it's like minimal possible concurrency in the kernel. And so then from there, you can sort of bootstrap, and I get more and more hand-wavy. And at the end, general SMP profit. So yeah, so from what I was talking about today, like there were some things I would have liked to get to in this talk, which was more SMP like user apps. So even though the kernels are partitioned systems, and it's easy to move a single threaded or a single core CAmkES app onto different cores, like projects like Barrelfish have shown that you can run full SMP-like apps at user level, where you can have multi-core apps running at user level, right? Yeah. And then more scalable cross-core notifications. They could do some investigation on the impact of like replicating kernel data structures and replicating page tables on shared caches, because you have a slightly larger cache footprint. And yeah, so at the moment, I still have to make the seL4 RPC call, which is one of the most common CAmkES connectors, work across cores. And then that's what I would need to be able to run a multi-VM, multi-core example, where you can run multiple VMs, pinning each one to a separate core, and potentially pinning some sort of filter or firewall between them on a separate core. And it should be good. Yeah, so I'll just skip this then. Yeah, but basically this is what I just said. Concurrent verified configurations only on a single core. SMP verified configuration still a long way away. Should be possible to support verified multi-kernel configuration significantly sooner. These restrictions from having a partition system may be less significant for static component architectures. and we can still have SMP in the future when it's ready. So it shouldn't distract from that. Thank you.
So there is a very cool idea here, and it's in particular in terms of getting to verification. There's actually this partition state thing makes a lot of sense, and it's probably not going to surprise you that I'm going to have opinions at you on this, and Gernot is too. So yes, there's some very cool stuff in here, but there's a few things that you're going to run into. Right, and again, if we can take this to an offline discussion where I think it's probably more productive to be on a whiteboard or something. But for example, your APIs suck. They're slow. They are going to kill you for performance. But more generally, actually more importantly, resource management is going to be awful, right? If you're partitioning like this, you do this static partitioning, right? Mm-hmm. So in particular, if you're setting up these, you're talking about using shared memory between the things on the different cores, right?
Yeah.
Right. So this shared memory, how is it accounted for in the capability system? Where is the capability for this? On which kernel?
It's in the, so if we go back. So basically, you could sort of say like each of these different CAPDL images have a different set of capabilities. So because they're partitioned kernels, you have each kernel is managing its own kernel state. So then,
so
I have a slide somewhere.
So the frame that's mapped to share between the two sides.
Yeah. So let's say
which kernel thinks it owns it.
So a frame that is mapped between two sides can only be, so let's say this frame.
Yeah.
It can only be created from this shared pool here.
Sure.
So seL4 currently distinguishes between two types of untypes. So it has kernel untypes and it has device untypes. Mm-hmm. So creating a shared frame, so sort of like creating a shared MMIO frame, each kernel allows you to create that frame and map that frame into an address space. But when you revoke it on one kernel, it's still going to exist on the other kernel because the authority is to add that physical address to the page table managed by each kernel.
Okay, so it's a sort of an external, like the synchronization of the resource ownership between these things, right? If you want to do any sort of dynamic validation or...
There's no synchronization of, like basically the kernel will only read and write to the resources that it owns, which is in this region. And then for things that are shared frames, the kernel allows you to create mappings for them in the address space. And in some configurations, the kernel allows you to flush or clean or invalidate the caches. And in other configurations, it doesn't let you because it's device untyped. And there is definitely a bit of a can of worms there about whether or not the kernel needs to let you perform cache maintenance on like these device untyped regions. But that also applies to like current kernels as well.
But both kernels have a capability referring to this object.
Yeah.
But they're not coordinating in any way on its use.
Correct. So I guess what are you thinking about when it comes to like a reason why they would need to coordinate?
It's just static. Yeah. I mean, as soon as you get dynamic, this is going to fall over, right?
Yeah. Well, as soon as it gets to dynamic, you're going to have to start building protocols at user level. Yeah. And if you're trying to and it only works with frames as well. Like if you're sending it, if you can't send a kernel thread across to another core, because the kernel would have to trust something from outside itself.
You can't.
Yeah.
Okay, because others may not heard, the disconnect here is that this assumes a static view of the world because it is built on CAmkES, so there's no dynamic resource management involved here at all. I just had one comment for you. Great work, by the way. That's the first comment.
Thanks.
The second one, part of what I hope to get out of, and I'm not sure I'll get it, but I hope to get out of our locking work is a clean way to get rid of cross-core IPC. So I'll pop a bottle of champagne when we manage to do that.
Yeah, I just reiterating what Gernot said, this is really good work. And also I think it's really appropriate for what we're doing, just our use cases in aerospace, which
Right.
are static, and this aligns, the multicore, the multi-kernel approach aligns much better with current certification regimes than the SMP approach. So we would be much more likely to adopt this anyway.
Yeah. Okay. Interesting. So it's like we're definitely trying to come at it from a systems point of view and try to being prepared to contort ourselves as much as we can to make it work for the verification. And like the hardware, like different hardware implementations have different perspectives on whether they're SMP or AMP, and I don't even know enough.
Things popping around across the board.
Maybe this work is more targeted towards classes of systems that don't require thread migration across cores. Is that something you thought about? And are like, the read operations on those kernel objects, like for VCP, you might need new read operations to do that. Is that something you've thought about? And is that something that is part of this work?
So it should be possible, even on a unicore system, to serialize the state of something like a vCPU object. And if you can serialize the state of an object, which is, read it out of the kernel, you can then, on a distributed system, send it across to another core, load it up again, and then start running it. And so in the absence of a system mechanism for just moving something across a core, you have to read it out, send it across, manually write it back in again. And so there are definitely things like vCPUs where the kernel, you can't do that at the moment because the kernel doesn't give you the ability to read out the full object. But I would argue that that's already a mechanism that's missing from the unicore system, because you would reasonably want to be able to read that out to suspend a vCPU and then resume it again later.
That's a good point.
Hey, I just wanted to comment from the verification side on this. This is actually very, very cool for verification because, not just because this is the simple case, but because it allows us to incrementally update the framework to a more concurrent one. So if you were to attack the SMP kernel directly, we'd basically be working for 3-4 years with no visible output, because everything is internal to the proof. You change your verification framework, everything's concurrent now, you churn through the proofs, and maybe at the end you get a verified kernel. With this, what you can do is basically, like Ken said, in the beginning it's hand waving, right? He made a convincing argument that everything's separate, therefore the proof should still hold. Formally, well, there's nothing there, but we can convince ourselves that, yes, this is a good argument. And we can step by step make this argument formal. For instance, by first of all proving that things are separate, then proving then that if they are separate, they will stay separate. Then we can move to a little bit more concurrency and say, when the kernel does a step, any other kernel might do a step now. And then finally, we can move to a model where there's true concurrency, where multiple users, multiple kernels execute fully concurrently in the model, and then observe that everything stays nicely. And once we have that, adding SMP is much easier than before. Then we're at the stage where we can add features, basically. So this is both from the system side doable, and from the verification side, there's already like, I don't want to say a fully thought out roadmap, but a fairly detailed roadmap for how we get from 0 to SMP with that.
Just a comment that there is an intermediate architecture that you have not talked about, which is when all but one of the kernels is running like a thinner, seL4 is already thin, but even thinner layer, right? That's linked with the secure domain. And you can even do dynamic distribution from the kernel locked in one of the cores. So basically one of the cores becomes master and all of the others are executing within their security domain. You can even do dynamic distribution of the tasks with their capabilities. And if, like, say, 2 cores are working on the same security domain, they can have direct IPC link that allow them to do. So you can have the global lock when you need it. You can have the local lock for the specific core, or you can have the local lock for the security domain. You can have multi-level locks so that you avoid locking everybody in order to do something, unless you really need to lock everybody in order to do something. It's like a master-slave kind of structure. We do that with multi-DSPs.
Right.
So it's like an intermediate between the two that you're, and it still presents one big SMP to whoever's programming because it's gets so distributed by the master system. And it's much easier to prove because now you have a master lock.
Right. And so that is always the same core.
Yeah, it's the core, the kernel-based locks a core,
Right.
right? And you would think, oh my God, resources, and we have now processors with 100 cores.
Yeah, yeah. One thing that got dropped out of the talk was like you could build a capability in seL4 to be able to spawn and revoke other cores, which is that similar to that architecture where you do have a single core that can spawn other cores and give the resources to those cores as they create them. And then when you want to redistribute, you revoke it, and it's a much bigger operation. And I think the original Michael von Tessen's kernel might have even had that, but I'm not sure. But yeah, like, I mean, it's sort of in that category of if we were going to step in the other direction away from SMP, then that would be something that we could do to make the, AMP style system work better. But, for another presentation.
Hi, thanks very much for a great talk. So with a single core seL4 system, a lot of the residual risk in the whole system sits sort of at the hardware level because we can't say too much about its behavior. With this sort of partition multi-kernel system, would that introduce new risk at that layer? Would that change the sort of our understanding of how we interact with it? And would that introduce risks that we previously didn't have to care about?
I mean, I might not have all of the expertise to answer this, but at one level, there is more surface area because you're going to be touching more hardware state that is dealing with multiple cores. So I think like one example is the like TLBs. So, if hardware is assuming that you're only building SMP systems, the ACID, so the ID of an address space might be being shared across cores without you knowing about it and without the ISA specifying it. And if you want to know more about that, talk to Dave, because I'm just parroting what he was saying to me last night. If you give me the microphone, I can give you example. But it's you wouldn't run into that on a unicore system, even though it was there. But now that you are using more hardware resources, you're more likely to run into them because they're more surface area.
So, I mean, the answer to your question is that you're right, is that there are cases like this. And one specific one I know of is that on ARM, it's now documented, it didn't used to be, that it is assumed that the virtual to physical mappings within an ACID, within an address space, are consistent among cores, right? You can't map the same VA to a different PA on a different core within the same ACID, right? If you have completely partitioned kernels that aren't coordinating, you have no way to enforce this.
Unless you partition the ACIDs, right?
Unless you partition the ACIDs as well, then you can never, yeah.
Yeah.
But this is an example of the sort of thing which will come up, yes.
Yeah.
All right. Any other questions?
I guess even more flavors of ice cream. Is it possible in the future we may have implementations where it is both multi-kernel and SMP, multiple SMP kernels at the same time? I mean, today we have some of these chips where one chip on a modern Linux box is using NUMA because the memory address, the memory is so distributed across the single board that read times and write times are so high that we have to take that into the operating system level.
Yeah, so the SMP kernel is designed for like small, closely coupled cores, and scaling above that to NUMA systems, the expectation was that you would use a multi-kernel-like system. So that PhD I talked about, Michael von Tessen's PhD, was called the clustered multi-kernel. So clusters were, within a cluster, it was an SMP kernel with a big lock, and then multi-kernels across clusters.
The important point here is the SMP kernel is not ever meant to scale beyond a small cluster, because as I said earlier in my talk, it only makes sense to have a single image in the seL4 world, as long as your cache line migration latencies are small compared to the system core cost. And so you're basically going to be restricted to systems that share an L1 and L2 cache, or at least have very fast L3 transfer, which, for example, x86 doesn't have.
Okay, I think that puts us at time. So once again, thanks to Kent, Lucy, and Wolfgang.